Welcome to Section 5 of Introduction to Image Processing. This section is about image segmentation, which means organizing the pixels of an image into groups. To describe the basic idea of segmentation, here is an image that could be separated into segments by separating out different colors or by looking for outlines of regions or in various other ways. One way, which mostly picks out the white clouds, is to segment the image based on brightness. This is an RGB image where one measure of brightness is the mean of the amounts of red, green, and blue in each pixel value. This input uses ImageApply to apply a function that calculates the mean of the RGB pixel values, and where that mean is bigger than 0.6, it replaces the pixels by 1, and everything else is replaced by 0. The result is another image that can be used as a separation of the original image into a bright segment and a dark segment, with the bright segment identified by the white pixels and the dark segment identified by the black pixels. The number 0.6 in that input is the threshold that separates the pixels that will be part of the bright segment from the pixels that will be part of the dark segment. Picking out parts of an image like this using a threshold is called thresholding. Here is a manipulate that provides a slider for adjusting the threshold. Setting the threshold to 0.6 picks out the brighter parts of the image. Increasing the threshold makes the image darker as more and more pixels fall below the threshold, and decreasing the threshold makes the image lighter as more and more pixel values fall above the threshold and transform to white. As a simple application, consider working out the fraction of the image that shows white clouds. This can be done by starting with the earlier input that picks out the bright parts of the image, which is mostly the clouds. The result is a black and white grayscale image where the image data is an array of ones and zeros, so totaling up the image data gives the number of pixels in the cloud segment. Setting the threshold to 0.04 segments the image in a different way that separates the foreground from the background. Totaling up the image data for this result gives the number of pixels in the entire disk. Dividing those two numbers gives the desired result, which is the fraction of the disk that is occupied by clouds. The operation of converting an image into an array of ones and zeros is called binarization. In the example so far, this has been done using the general-purpose ImageApply function, but there are specialized tools for binarizing an image. In the Wolfram language, binarizing an image can be done using the binarize function. The first argument in the binarize function is the image, and the second argument is the threshold, so this input binarizes the image with a threshold of 0.6. For binarizing an RGB image, the binarize function actually uses a weighted average of the red, green, and blue pixel values rather than just the mean, but the basic idea is the same. It is sometimes useful to binarize an image by giving both an upper and a lower threshold to pick out a range of pixel values. For example, here is an image showing objects with different shades of gray. This uses the binarize function with the second argument specifying the range 0.5 to 0.7, which picks out the gray objects on the left since the pixel values for that shade of gray happen to fall in the range between 0.5 and 0.7. Other choices for the threshold values can be used to pick out other parts of the image. For example, this picks out the objects on the right, which have pixel values that fall between 0 and 0.5. This picks out the background of the image by picking out pixels with pixel values greater than 0.7. Now that the image has been segmented, you can do whatever you want with the segments. For example, this combines the three segments into a single RGB image. Choosing a threshold interactively or by trial and error is often impractical, especially in applications that involve processing a large number of images, so it is common to want a way to have the computer choose a threshold automatically. There are several common automatic methods for choosing a threshold. For example, the threshold could simply be the mean or the median of the pixel values in an image. Other methods include specifying the fraction of pixels that should be black, or choosing a threshold using a method known as Atsu's method, which picks a threshold to minimize the variance of the pixel values above and below the threshold. For example, here is an image to binarize. The mean function, when applied directly to this image, returns the mean pixel value, and this binarizes the image using the mean pixel value as the threshold. The same result can be obtained using the method option of the binarize function. Setting the method option to mean gives the binarization using the mean pixel value as the threshold. A method that works well in this example, at least for the purpose of separating the foreground from the background, is the cluster method. The cluster method works well in examples where the image histogram is bimodal. Here is the image histogram for this image showing a bimodal distribution of pixel values with a cluster of dark pixels for the background and a second cluster of lighter pixels for the light-colored animal in the foreground. Here is a manipulate result that has been set up to show the effect on this image of different ways of choosing a threshold, such as using the mean pixel value or the median pixel value. Specifying the black fraction can be useful in applications where it is more natural to specify the fraction of pixels that should be below the threshold, rather than specifying the threshold directly. The cluster method works by finding the threshold that minimizes the variance of the pixel values above the threshold plus the variance of the pixel values below the threshold. This is a strategy that is really designed specifically to put the threshold in an optimal position between the two clusters in a bimodal image histogram, which is why that method works well in this example. The cluster method is the method that the binarize function uses by default if the threshold is not specified, so this input gives binarization with the threshold chosen by the cluster method. You can also calculate the threshold value by itself using the find threshold function. For example, this calculates a threshold for the image giving the mean pixel value as the threshold. This is the same as calculating the mean of the pixel values in the image. You can also get the thresholds for other methods. For example, this gives the threshold that is used by the cluster method. One common challenge in choosing a threshold is illustrated by this example where the best threshold is different in different parts of the image. To illustrate the problem, here is a manipulate input that such as might be used to choose the threshold interactively. The goal of binarization in this example is to improve the readability of the text. A threshold of 0.6 works well for the lighter parts of the image, but makes the darker parts of the image completely black. A lower threshold works well for the darker parts of the image, but makes the lighter parts of the image completely white. One potential way of dealing with this problem, which is rather cumbersome but sometimes works, is to partition the image into pieces that use a separate threshold for each piece. This image is 2000 pixels wide, so this image can be conveniently partitioned into 4 pieces. Then binarize each piece separately so each piece can use a different threshold, and assemble the result into a single image. In addition to requiring some ad hoc programming, this approach tends to leave edges at the boundaries between the parts of the image, but the basic idea of using a different threshold in different parts of the image is still a reasonable idea. One solution to these problems is to use a different threshold for every pixel, and to determine the threshold for each pixel based on the values of neighboring pixels. For example, zooming in on a small part of that image, this shows a 7 by 7 neighborhood around a typical pixel. The pixel to be binarized is the pixel in the center, which is sometimes called the origin of the neighborhood. One reasonable choice for the threshold is to simply use the mean of the pixel values in this neighborhood. The pixel value for the origin pixel in this example happens to be slightly smaller than the mean, so the original pixel would be replaced by black, which makes sense since that pixel is slightly darker than most of the other pixels in this neighborhood. The entire image can be binarized by applying this strategy to every pixel in the image. In the Wolfram language, this strategy is implemented in a function called local adaptive binarize. The second argument in the local adaptive binarize function specifies the size of each neighborhood. The value of 20 here specifies neighborhoods that extend 20 pixels in each direction from each origin pixel, so this uses a 41 by 41 neighborhood around each pixel. This is called a locally adaptive process because the process naturally does something different depending on the local neighborhood around each pixel. There are 2 important details to consider to make effective use of locally adaptive binarization. One of those details is the size of the neighborhoods. Here is a manipulate input that provides a slider for adjusting those sizes by adjusting the second argument in the local adaptive binarize function. The size is typically adjusted to be large enough so that each neighborhood includes an adequate range of pixel values, but small enough so as not to blur features of interest. In this example, a neighborhood extending 20 pixels in each direction works reasonably well. A second detail to consider is the formula that is used for choosing each threshold. So far, the threshold has been the mean of the pixel values in each neighborhood, which is what the local adaptive binarize function does by default. In this example, using the mean works well near the text, but away from the text it gives a background that is speckled black and white rather than being completely white. The speckled black and white background happens because when all of the pixels in a neighborhood are almost the same shade of gray, then the origin pixel will almost randomly transform to either black or white depending on whether it is slightly darker or slightly lighter than the average pixel in that neighborhood. For example, zooming in on a typical background pixel shows a neighborhood where it is not obvious if the origin pixel should transform to black or to white. The effect is for pixels to become black or white essentially at random, which gives the speckled background seen earlier. A result with a white background can be achieved by lowering the threshold so that a pixel only turns black if it is significantly darker than neighboring pixels. This can be accomplished by including 0.8 as the third argument in the local adaptive binarize function. With that change, all of the background pixels transform to white. That lowered threshold also works well for the neighborhoods that include text. You can use the manipulate function to set up a slider for trying other multiples of the mean. The third argument of the local adaptive binarize function can more generally be used to specify that thresholds be calculated using any linear combination of the mean and the standard deviation of the neighborhood pixel values. So far, all of the segmentation has been done by thresholding, but there are many other methods of segmentation. For example, this shows a method called region growing, which is implemented in the Wolfram language with the region binarize function. Region growing starts with an initial region called a marker and binarizes the image to separate out the region that is connected to the marker. This example uses manipulate to get a slider for adjusting a parameter that specifies which pixels will be treated as part of the segmented region. Here is a different image which has been segmented using the clustering components function, which uses a method called clustering. This particular result segments the image into 7 components. The output is a matrix called a label matrix, which is a common way of representing the segmentation of an image. The colorize function is used here to display the label matrix as an image with different colors for each segment. The label matrix itself is an array of integers. It is a large array with the same dimensions as the dimensions of the image, but you can scroll into the array to see the integers. This image was separated into 7 segments, so the array elements are the integers 1 through 7, with 1s for the pixels in the first segment, 2s for the pixels in the second segment, and so on. The result from binarization is also basically a label matrix. The output of the binarize function displays as an image, but for most applications the image is not really needed since the analysis is done on the image data. The image data for a binarized image can be thought of as a label matrix, where the 1s and 0s label which pixel is in which segment. Beyond these few examples, there are many other methods of segmentation, some of which will be described in later sections. That's the end of the examples for this section. To summarize, here is some of the vocabulary from this section. Segmentation is a critical step in many image processing applications.